Hello, RJ the Scholar here. Now here for a new YouTube series. How to destroy your opponents with facts and logic. Episode 1, Propositional Logic. So, you want to learn how to defeat your opponent? That opponent being false reasoning, right? Sorry if you thought something else. So, what we're going to learn? What are we going to learn? He told us we're not going to learn about how to defeat opponents. Well, I'm going to teach you how to defeat bad things, falsehoods. So, this class is about facts or lies and how we can make new ones. This class is also about logic, which allows us to find new facts from old facts. So when I say we are going to learn how to defeat your opponent with facts and logic, I technically wasn't lying, which is the best kind of not lying. So, here's the plan. This first episode, covering propositional logic. Next one, logical equivalencies. And the next one, we're going to be covering predicate logic. And as an A-side, we'll be covering nested quantifiers. We'll also be doing inference and fallacies. And finally, we'll conclude with techniques of proof, which will bring all this stuff together. So, this episode's goals is to introduce you to propositions, teach you about logical operations, or Boolean logic, and teach you how to convert from English sentences to logic. So, let's learn about propositions, which are the facts, and nothing but the facts. Language. Say we have a fact. The Earth is round. Here's another fact. I can see Aurora Australis. This is a statement that depends upon where I live, which means it does no definite truth. You can say it, you might be able to see it. I can say it, I might not be able to see it. So, it has no definite truth. So let's not consider this yet. And here's a lie. The Earth is flat. We want to find a way to describe facts and lies. So, let's introduce something. So we want a general idea that encompasses statements that are true or false, but not statements that could be both. I think we have our definition. A proposition is an exact statement that is either true or false, but not both. That's very important. Stuff like that has variable truth value, we don't use that as proposition. However, that's a little later on. We're going to be covering it, but not today. So, examples of a proposition include 2 plus 2 equals 4, which is true. X to the 4th is less than 0, which is false because x to the 4th is always greater than or equal to 0. 0 equals 4 because it's not. And Paris is the capital of France in 2021, which is true. However, x to the 3rd is less than 0 is not a proposition, as it is true if x is less than 0 and false otherwise. That means it has variable truth value and therefore is not a proposition. So we have propositions. Now what? Well, remember algebra? Where numbers turned into letters? Yeah, propositions are now going to be letters. What fun. So we can say, for example, P, well, there's a special symbol there. What could it mean? Well, it means is defined as. So this is P is defined as the Earth is round. So we have letters standing for propositions, and those are called propositional variables. So let's use these variables in the abstract, ignoring their value. But first, we gotta learn about truth value. I've been throwing it up around there, but now I'll explain it. It's really simple. So we have a proposition like before, the Earth is round. The truth value, whether a proposition is true or false, of P is true. That's all the truth value means. Nothing else, nothing more. So whenever you see this phrase, just remember, it's just whether it's true or false. Sometimes true is represented as a T, or this weird T, and the false is represented by an F, or an upside down T. But I'll stick to using T or F. I just introduced them because some people like to use the different orientations of T, which can be very not confusing, but not good. Okay, why am I telling you this? It's to be connecting to you logically, which is a segue to logical connectives. And or not XOR implies an equivalent. What are those? We'll find out. So, we've been dealing with only the most basic of propositions, which are called atomic propositions because we can't divide them any further. That's why I said one proposition, indivisible, and truth for all in the top. But there's no logic if all we can say is if this thing is true or not. That's just saying, oh, is it true? Well, let me rely on my pre-knowledge, pre-knowing knowledge. There's a better word. There is. But I'm not going to use it. But it relies on prior knowledge, which it's useless if we just have prior knowledge. We're not learning anything. What's the point of logic if we're just saying things we already know? So we need some logic to connect these propositions, get it, logical connectives, so that they aren't just words that are either true or false, but not both. Remember that? I'm just going to reiterate that. So we have logical connectives. There are 6 main logical connectives. Not, and, or also called a conjunction, or disjunction, XOR, or exclusive disjunction, implication, and biconditional, each represented by those symbols. A proposition made using these connectives is called a compound proposition. So, truth tables. What are they? We'll use a tool called a truth table to analyze these logical connectives. One column for each input and one from the output. And we're allowed to have intermediary steps. We are required to have one column for each input and one for the output. We need a row for each possible input in the truth table. So, how many rows do we need? For every propositional variable used in an input, there's like 2 values it could be. So, 2 values times 2 values times 2 values times 2, etc., etc. The total number of rows needed to list every input has got to be 2 to the number of variables. And here's an example of a truth table. You see here, there's an input, and here's an output. So I'm going to explain a little about how we fill in like the inputs. First, we set half as true and half as false. And that if we have another variable, we set each half that we designated for true or false as true and false. It's kind of like a fractal, if you've heard of them. So you'd have, like, if there's 3 variables, there would be 4 truths, 4 falses for the first variable, 2 truths, 2 false, 2 truths and 2 false for the next variable, and then true, false, true, false, true, false, true, false for the final variable. That's how we typically fill it out. It's like counting backwards in binary, if you're familiar. So let's counter the first one, negation. We want to be able to deal with statements like the sky is not green. This is the job for negation. So the negation of a proposition is true if and only if the proposition is false, and vice versa, which is represented by a sort of tick like this in front of the proposition, and also called not. So here's a truth table. See, we have the input and we have the output. Let's write our first input. It has to be a true, right? Because the first half is always true. The second one has to be false. So we have that. So not P will just flip the truth value. So T turns to F and F turns to T. There's only one input here, so we need 2 rows in the truth table to get all the inputs. So here's a little translation tip. Not is just a not. There's no tomfoolery here. When you see not, it always means this. Unless you can, if you can find me an example where it's not true, please tell me in the comments below. So we have, if the sky is green is false, the negation of our statement up here, then the sky is not green must be true. So this is a true statement because the sky is green is a false statement. Now, we're going to have to deal with something crazier. Something with 2 inputs. So, what about statements like children are over 18 and under 25? Conjunction solves this. The conjunction of 2 propositions is true if and only if, there's that statement again, both individual propositions are true. It's represented by like an upside down V and also called AND. So we have these truth table. We need 4 inputs because there are 2 variables. And the first half of P will be filled by T's. The second half, F's. Don't get those on tests. Okay, so for Q, we alternate because half of each shall be like the first half of the true section of P is for T's. Second half for F's. First half of F's for T's. Second half of F's for F's. So that's how we do the system. So let's just evaluate it. So it's only true if both individual propositions are true. So the first line, true. Everything else, false. So here's a little translation tip. When one says this and that, it typically means that both this and that are true. The statement, children are over 18 and under 25, can be determined to be false by breaking it into smaller pieces. Remember those atomic propositions? And testing the truth value of each. Since children aren't over 18, we immediately know that it is false. That's a mouthful. You know what's not a mouthful? Having choices. Here, we have no choices. we can only pick 2 truths for this to be true. But next slide, we're going to be seeing about disjunctions, where you can pick one or both. So we have statements like a triangle has 3 sides or has 3 vertices. Disjunction solves this. The disjunction of 2 propositions is true if and only if at least one individual proposition is true. It's represented by a V symbol and also called OR. So again, we put the truth table. Again, we kind of have the same setup for the inputs. True in the first half, false in the second half. Repeat, remember, ignore this. And if this was just an individual truth table, we'll just use half of it each time. Like, half of the first half is just where P is true, the second half is where P is false. So we'd have to have a true and a false. That's how we do it. So, true, false, true, false. That's how we do it in here. So, luckily, it's only at least one. So if they're both true, it's fine. We're allowed to pick both. One? Okay, you're allowed to only pick one. The other one? Okay, sure. You can't pick none of them, though. That's cheating. So, there's a translation tip here. You gotta be careful. Remember when people say this and this or that? Yeah, they typically mean not this. They typically mean you can only pick one. This is not that. This is not for dealing with this. However, we do have a special connective for this. It functions much like the English OR. Well, we have the statement above to be true because a triangle is both a 3-sided polygon and has 3 vertices. So we're going to pick one. I'm going to pick an exclusive interview with you guys. It's going to be so exclusive. I'm only telling you about this. You could find this anywhere else, and it would be not with me. But you can only get this one with me. Okay? So, we're going to explain exclusive disjunction. Because we have statements like Jim is outside or inside, but he can't be both. So we need a new connective. Exclusive disjunction. So the exclusive disjunction of 2 propositions is true if and only if only one individual proposition is true. This is represented by a little circle and a plus in a circle and called XOR. This is kind of related to binary addition in computing. Like your hardware uses XOR for addition. And that's why it's the circle with a plus, because it's addition. And also, people call it XOR because everyone likes X's at the beginning. It just makes everything awesome. So, P and Q. This each half, the first half, we get T's. Second half, F's. Half of the first half, where the P is true, gets T. Second half of the true P's, it's F. First half, essentially we just divide in half. We just continuously divide in half. Each division, we flip the next variable. So, let's continue. At the beginning, this is the difference between exclusive disjunction and normal disjunction. If P and Q are both true, P XOR Q is false. If one's true, it's fine, but you can't pick both and you can't pick none. So this is what usually per person means when people say this or that. And the above is a true statement because you can't be inside and outside at the same time. Let's just say Jim's outside. And the implications of this are massive. Because we have to deal with statements like, if it is raining, then I need an umbrella. We can't really deal with if-then statements using just like our 4 earlier connectives. We're going to need a new one. Implication. So, there's only one time the implication P implies Q is false, and that's when P is Q and Q is false. When P is true and Q is false. I misspoke there. So, we have this truth table. Let's just fill it all with the usual jazz. Remember, half of it, true, you split it in half. That's the first time you flip, and then you split it in half each time, and then you flip there. That's how I think of it. So here's the truth value. First one, true. If they're both true, always implies true. But true can never imply false. Just think about it. If like this statement wouldn't be true if it was raining and I didn't need an umbrella. Like it simply wouldn't be true. But the opposite is not true. I may need an umbrella, but it might not be raining. And, well, false does imply false. It's not raining, so I don't need an umbrella. So, usually when one says if P then Q, it means implication. Also, if you see P only if Q, it also means implication. P if Q actually means Q implies P. You see if and only if? Well, today's your lucky day. That's actually something huge. But anyway, the above would only be false if it was raining and I didn't bring an umbrella. But I always bring an umbrella, so you don't have to worry about it. So, but first, we're going to have to cover some terminology. In P implies Q, P is called the hypothesis. This sounds dangerously like science. Oh no. But it's okay. And then Q is called the conclusion, which also sounds like science. In P implies Q, the hypothesis implies the conclusion. That's what they're called. It's just nomenclature. You don't have to call it that. You could just call it P and Q. But if you ever encounter them calling it the hypothesis and the conclusion, you heard it from me here first. So we have Q implies P, which is called the converse of P implies Q. It's essentially flipping the script. Well, if Q is P can't Q only is it's the reverse. Q can't be true if P is false, unless you want the statement to be false, which is bad. I'm trying to combat falsehood here. And then we have not Q implies not P, which is called the contrapositive. Yeah, it's weird. how there's this property. I'll tell you a little later after I introduce you to the inverse, because I want to get all this terminology stuff out of the way. It's essentially just nodding P and nodding Q, and it's not P implies not Q, which is just it has the opposite value. But the contrapositive always has the same value as the implication. Because think about it. Not Q implies not P. That means, like, if the only time it's false is when Q is false and P is true. Which is the same as the implication. Wow, isn't that neat? Remember this for later, kids. And now on to the biconditional. What about statements like a triangle is a triangle if and only if? There it is again. Ugh. Its angles sum up to 180 degrees. We need a new connective to deal with it, called the biconditional. The biconditional P by implies, because it's both ways, Q is true if and only if, there it is again, P has the same value, truth value, as Q. So we have the truth table, T, we do the same thing as before, T, first half, F, second half, then we have a division there, we flip at that division, so we divide it in half again, each one in half, flip at each of those divisions, T, F, T, F, and then we just evaluate it. When they're both the same, it's true. When they're different, it's false. Same, true. When someone says if and only blah, if and only if blah, it always means there's a biconditional there. If and only if always means biconditional. No doubt about it. Though the above could be false if the triangle were in non-Euclidean space, but that's for another class later. So, now what? We have the basic building blocks of logic. Now what? Well, we'll use the connectives to combine many propositions together. We're not just gonna have two things, just use multiple of them. But we have to clear up some things before we jump into some examples. So, we have a logical order of operations. We need that. Before we start combining connectives, let's first try to set an order to which we do them. Because you have to remember, like, the arithmetic order of operations, PEMDAS. So, reverse is always parentheses. Because parentheses always goes first, because parentheses just denotes a special order to which we do things. This is to essentially a logical order of operations is just tells you where to put the parentheses. All else is just a consequence of our order. The first up after parentheses is negation, because we always apply that first. So if you have if we have the symbol not, and then we have P, and then we have the symbol for and then Q, it would not apply as not P and Q. It would be not P and Q. So we also have conjunction next. So that and always goes first after doing any unary operations. Then we do disjunction, which is or. Then we do implication, and then we do the biconditional. However, we will liberally use these parentheses to reduce ambiguity, because they always come first. So let's look at an example. But you know how please excuse my dear Aunt Sally is a nice mnemonic for PEMDAS. I came up with one up with my own of my own. It's good. It's actually pretty funny. Well, it's pretty new cheese dissolves in bile. It's just a little funny thing. Anyway, let's go on to the first example. Let's look at this compound proposition. Not P, and not Q. Let's look at the truth table to analyze it. Because the truth table this is the main method for which we're doing analysis of logical connectives. Because there's no real easy way to talk about them otherwise. So we'll set up each row. So we have the inputs P and Q, and for each different operation, sub-operation, I do an additional step intermediary step in between it, just to be it's nicer. So we have P and Q first. First we have T, the true, then we do the same thing. It's 4 things because there's only 2 variables. Same dang flip-flop motion. And then we start applying logical operators. So not P, we're able to figure out just by flipping the P value to the opposite. Same with not Q. And then we just basically have this upside down, which is nice. So now we have not P and not Q. So that's just F, 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 F. Hey! Doesn't this look like that? This is when both are false. So this is just kind of like an upside down and. But when we not this upside down and, wait, doesn't this kind of look like an or? Yeah, that's right. It's exactly or. But that truth table example, it kind of works with our truth table skills. But let's move on. Let's do a little practice run. So we have let P be defined as, we'll just say let P be plants or animals, Q be a chicken as a bird, and R be birds or animals. So let's determine the truth value of Q implies R. I'm gonna pause for a second so that you might be able to figure it out. You could pause the video if you want to have a little more time. And time's up. It's true. The reason is a chicken is a bird is true, and birds are animals is true. So the statement, it's true. But what about R and P? Well, let's look at the truth value of P. Plants are animals. I'll let you decide whether it's true or false. I'll pause for a little bit. Okay, if you want more time, you can pause it, but I'll give you the answer now. It's false. And so we know that R is true from before. And a true and a false is what? Pausing again. You can always pause the video. Okay, it's false. Remember, and requires both to be true. Now we have the special P XOR Q. Plants are animals. XOR, a chicken is a bird. One's true, one's false. Pause for more time. And the answer is true, because XOR requires that one is false and one is true. Okay, now we have P implies R. This one is a tricky one, but if you remember from before, there's only one case where this is false. I'll pause to give you some time to think about it. And it's true. Because even though plants aren't animals, the fact that birds are animals, so it's true. The only way it's false is if the thing does, if the proposition is true, the hypothesis is true while the conclusion is not. And finally, this beast. Remember last slide? Remember that truth table? Remember what the by implication does. P or Q matches exactly with not this thing. So, what's the truth value of this? I'll give you a second to think about it. Pause for no more time. And it's true. Because since they have the same values, then no matter what, the biconditional is true. Because they both have the same values. So that's all the practice for like the proposition stuff. But now let's translate into propositions. And the question is, why would you translate from English? Why? Well, you can explain something in English well, and you may convince someone. But having it displayed logically is, of course, rock solid. That's why it's used in philosophy, law, and verification of like some specs. Like if your boss tells you to do something, you can make sure like that the things aren't contradictory. And there's always more applications of this. So here's our second example. You can beat me in a debate only if you watch all the series or you have taken a class in logic. The process of translation is simple. First, you find logical connectives, and you find the atomic propositions and assign a propositional variable to it. And finally, you combine the propositions according to the connectives you found. So, same example. We'll circle the logical connectives in red. Right here, you see the circles right there. And then, because only if, that's a logical connective. Remember, it means the implication, and or means or. And then we'll use the divisions created by connectives to find the atomic propositions. So we'll let P be, you can beat me in a debate, Q be, you watch all the series, and R be, you have taken the class in logic. So let's combine the propositions according to the connectives. Or only if means implication, or means or. And so we have P implies Q or R. Okay. On to our third example. This is our final example. So if this video is getting a little long, you'll be able to take a break. And that's it. So if you do not watch all the series and you have not taken a class in logic, then you cannot beat me in a debate only. That's a mistake right there. That's an extra word. Copy pasting nightmares. So we'll just circle the logical connectives in red. And we'll use the divisions created by the connectives, then doesn't count. To find the atomic propositions. Actually, you usually don't consider not as a division. I wouldn't consider not as a divider. Not is not a divider. It's a special one because it's unary. It's just it's a special saying to flip it. So we'll just do that, and we'll use it. So the if then is like saying the if after the if is like the first half, and the after the then is the second half of the implication. It's still one operator, but it is a little different than that. So we'll divide it appropriately. So let's say P is you can beat me in a debate, even though it's at the end. Q is you watch all the series. R is you have taken a class in logic. So, you may be familiar with this. Combine the propositions according to the connectives you found. So, we have to negate Q, and then we have to negate R. So, not Q and not R, because we have that and there. Not Q and not R implies, because we have the if then, not P. Hold on a minute. Hold on a second. Remember the previous one? It was not P. P implies Q or R. This is the contrapositive. I said this would come in handy. I said it would. But no, it actually comes in handy more, actually. A little later on, actually next episode, we'll be talking about logical equivalencies. Contrapositive and implication being the same. It's very important. Speaking of next episode, this is the end of this one. So, propositional logic is just a simple tool for reasoning. However, we do need to cover one more thing, which is logical equivalency, before we are masters of it, and we can move on to a better logic, which is called predicate logic. So do you notice how the negation of the conjunction of two negated propositions is just the disjunction of the propositions? Wow, that was word salad. Well, that's what we're covering next time, but in symbols, which is always more clearer than word salad. So, that's just next time in Math 100, Facts and Logic. See you next time!